All right, guys, welcome back to our discussion on complex numbers and completing the QM.1 notes. So in the last video, we talked about imaginary numbers and looked how we could use the value of I to simplify roots that we once thought could not be simplified. And also we looked at multiple powers of I. And in some of those examples, at the end, we talked about what a complex number was, or saw an example of a complex number. So let's go ahead and let's define complex numbers. So a complex number is the combination of any real and any imaginary number. Generally, how we write this is in the form a plus bi. And this is where a and b are real numbers. So this first term a is going to be a real number. And technically, remember b times I, that put together is an imaginary number. The b would be telling us that there are multiple values of I. So there's two i's if b is t, or two if there's three i's if b is 3, and so on and so forth. And so this is what we talk about with imaginary numbers. So remember when we talked about graphs of equations that did not have solutions? Technically what we looked at was on the real number line, the Cartesian plane which we're used to seeing. There is another plane that exists. And this plane, it's called the complex number plane. So on the x-axis, we have real numbers. 1, 2, 3 to positive infinity, -1, -2, -3 to negative infinity going to the left. On the y-axis, we actually have imaginary numbers. So what we would have is I, 2i, 3i, going up to infinity numbers of I. And then down below the x-axis, on the y-axis, we'd have -I, -2i, -3i, and so on and so forth. So if we took a look at an example, a number that does not exist on the real Cartesian plane that we're used to seeing, let's say maybe an example would be 3 plus 2i. We can actually graph that solution. That solution would be 3 on the x-axis and 2i on the y-axis. So that point, that solution does have a location. So even though we have solutions that we could not graph on our normal xy coordinate plane, dealing with all real numbers, now in this complex plane, we have solutions that we can graph with complex numbers. Let's say we have 2 minus 3i. Well, what I would have here is positive 2 on the x-axis and negative 3i on the y-axis. Okay. We won't really do any graphing of these. I won't expect you to know the complex number plane, but this is just an example of how some of these solutions can actually show up on different types of graphs. What I do expect you guys to be able to do is deal with complex number arithmetic. So we're going to look at addition, subtraction, and multiplication of complex numbers. So let's take a look at example 6. In 6, the directions say perform each of the indicated operations and write the result in the form a plus bi. This is like standard form for a complex number, what we saw on the previous page. So an imaginary number, a real number plus an imaginary number. So in 6a, we have an addition problem here. We have two complex numbers that are shown in parentheses, two binomials, and they are added together. So similar to variables, we can treat I as a term, and we want to combine like terms. So if I remove these parentheses, what I can do is kind of rearrange. The parentheses aren't important here because there's nothing to simplify inside either parenthesis. So what I can do is I can rearrange. I can take 3 and 7 and add those together. And then I can take, sorry, I need a plus in there. So let's have 3 plus 7 plus 4i. And then I can combine the 4i with the negative 20i. So now similar to, again, arithmetic with variables, we want to add and subtract the like terms. So 3 plus 7 would be 10. And 4 minus 20 would be negative 16i. And this would be our final answer. So it is in that complex number standard form. A plus bi, here's our real number. Here's our imaginary number. And so that's in the correct format. Okay, so we can treat I as a variable or the same concept as a variable when we add and subtract. So now let's take a look at B. Here I have a subtraction problem, so I do want to make sure I simplify first by distributing this negative. So I'm going to have 3 minus 7. And then I'm going to have 4i. The negative times the negative would be plus root 2i. So 3 minus 7, I can combine those. This is going to be negative 4. 4 plus root 2i. These are like terms, but I can't combine 4 and root 2 because we're adding a whole number with a radical. And remember from Algebra 1, we can't do that. So how I'm going to represent this is I'm just going to put 4 and 2i together, or sorry, 4 and root 2 together in a set of parentheses, and then I afterwards. And this would be my final solution here. So I would have my a value there, my b value there, and then I at the end. Taking a look at C, we have some multiplication in C. So to simplify this, we're going to need to distribute. So 6i times 2. Again, thinking of I as the same concept as we would at arithmetic with a variable, we can multiply the coefficients. 6 times 2 is 12, and so we'd have 12i. Now, if I distribute here, what I would get is 6 times 3, so positive 18. And then I times I. I times I would give us I squared. And so now here we run into a situation where this is close to real number, but it's not quite a real number. Think back to the previous video and what we talked about in the notes in class. What is the value of I squared? Well, even from the definition of an imaginary number, we can replace I squared essentially with negative 1. So we had to have 18 times negative 1. Now I can simplify. 18 times negative 1 is negative 18, and I'm going to put this first, plus 12i. So I put the negative 18 first because that's my real number. That's my a value. Here's my b value, and there's I, so my real number plus or minus my imaginary number. So what we see here is that I squared can be simplified into negative 1, and that goes back to the definition of an imaginary number. This is something we're going to see occur over and over, so we got to get used to seeing that I squared and replacing it with negative 1. Let's take a look at another multiplication problem here, 6D, where we can distribute again. So I can take 1 times 1 is 1. I can take 1 times negative 2i, that's negative 2i. I can take 2i times 1, that's positive 2i. And then I can take 2i times a negative 2i, so that would be negative 4i squared. Now as I simplify, my 1 doesn't have anything to combine with out here in front, so I'm going to just keep that. My negative 2i plus 2i, those would subtract out and give me 0. So now I have 1 minus 4, and remember we can replace I squared with negative 1. So this is 1 minus 4 times negative 1. 4 times negative 1 is negative 4. So 1 minus negative 4 would be 1 plus 4, which is 5. So this is my final answer here. It is actually just a real number. There's no complex number here because my b value actually became 0 when I added and subtracted these two i's together. And so now I just have a real number. This is going to be an important concept that we look at later on. So we're going to come back to D. If you get the concept, go ahead and pause the video and see if you can solve or simplify in problem E. Hopefully we've gotten a chance to take a look at E. So let's go ahead and complete this. Let's distribute. So 3 times 4 is 12. 3 times 7i is 21i. Negative I times 4 is negative 4i, and I'm going to go ahead and just line those up. And then negative I times 7i would be a negative 7i squared. Now if I combine these like terms, this is 12 minus 2I minus 7 times negative 1. Remember, we can replace 7 with, or sorry, I squared with negative 1. So this would be the same as 12 minus 2I plus 7. I can combine my 12 and my 7 to get 19 minus 2I. And there we have our complex number. Now, in F, we have a lot more going on here. We have some multiplication we can see in there. We also have some subtraction. Remember, this is simplifying, so we have to follow the order of operations. So the order of operations says to work inside parentheses first. If we look inside the parentheses here, in each one, there's nothing we can do to simplify. Exponents would come next. We don't have any exponents. So now we need to multiply. So let's go ahead and do some multiplication. It's going to be a little complicated, but that's okay. Let's take 3 times 4. We get 12. I'm going to put this together in a set of parentheses just to help us with order of operations. 3 times 4 is 12. And then I'm going to take 3 times 7i. This is positive 21i. And then I'm going to take negative 1 times 4. That's negative 4i. And then I'm going to take negative I times 7i. So that's negative 7i squared. Now over here, I'm going to distribute my negative 2. Or I can just distribute the 2. Let's go ahead and just distribute it as a negative 2. So that would give me negative 2, negative 2 times 1, and positive 6i. Now, the reason I put this first one in parentheses is because we just multiplied all of these together, and then we're going to subtract this multiplication. So when I distributed the negative 2 through there, I went ahead and took care of the subtraction, so I can list those just as terms. Really, what I could see here is that maybe I don't even really need parentheses on that first one. So let's eliminate those, because the way I did it, I distributed that negative 2, and so now I can combine my like terms. So let's combine like terms. 12 and negative 2 would combine together to give us 10. 2i plus 6i would combine together to give us 8i. Sorry, 2i minus 4i plus 6i. There's 3 terms with I. So we can combine all those together, and that would give us a positive 4i. Then I have this negative 7i squared, which I can replace I squared with negative 1. So this gives me 10 plus 4i plus 7. Now I can add my 10 and my 7 together to get 17 plus 4i. So still just simplifying, just a few more steps to take care of, making sure we follow order of operations. So when doing arithmetic, multiplying, adding, and subtracting values of I, we can treat I or follow through I with the same rules as we would any other variable. Let's go ahead and take a look at another example. 7a. In 7, it says, for each of the following, verify the given solutions exist for the given equation. So what this is saying is the solution for x is x squared plus 6x plus 13. That's the solution. Now, remember, as we talked about imaginary numbers, solutions are anywhere where a graph touches the x-axis. So if I graph this equation, we can see that it does not touch the x-axis. So what that tells us is there are solutions for the equation, but they're going to be either imaginary or complex numbers. So here in problem number 7, it tells us, gives us a complex number and tells us it is the solution for this equation. Well, we want to verify, meaning we want to show that this is true. So what we can do here is we can substitute in the value that they give us for x and see if this equation is going to equal 0. So the equation is supposed to equal 0. If it does, then this problem works. If it equals anything other than 0, then we know that this value for x is not a solution. So let's go ahead and let's substitute. So this is going to be negative 3 plus 2i squared plus 6 times negative 3 plus 2i plus 13 equals to 0. So remember, to square something basically means to multiply it by itself. So I'm going to rewrite this first term as negative 3 plus 2i times negative 3 plus 2i. just to make the distribution a little easier for us. And then I'm going to simplify. So negative 3 times negative 3 is positive 9. Negative 3 times 6i is negative 6i. 2i times negative 3 is a negative 6i. And I'm just going to go ahead and line up my like terms right now. I'm just going to line my like terms up as I multiply and then add all together. So I have 9 minus 6i. I just got another minus 6i. And then here I'm going to have 2 times 2, which is 4. I times I, which is I squared. I'm going to distribute my 6. So 6 times negative 3 is negative 18. I'm going to line that up with 9. So it's easier to combine the like terms in a little bit. Then I'm going to have 6 times negative 2i, which would give me negative 12i. And then I've got this plus 13 here that I'm going to line up there with the other whole numbers. So what we want is we want this to equal 0. Sorry, we don't know what it equals yet. So let me start to combine my like terms here. So 9, I'll show you this on the calculator. 9 minus 18 plus 13, combining all the real numbers together, is 4. Oh, sorry, I made a mistake. This should have been plus 2i. When I wrote that down incorrectly. So should add a plus 2i here in the second set of parentheses or third set of parentheses, which makes this a plus 12i. There we go. So now if I add together those terms of I, this would be negative 6 minus 6 plus 12, which we know is 0. So this would give me 0i. And I can bring down my 4i squared. Remember, I squared is just negative 1. So this is essentially 4 times negative 1, which is negative 4. So what I get is 4 minus 4, which is 0. So when I substitute in x for this equation, this is a solution. So x equals negative 3 plus 2i is a solution because it allows that equation to equal 0 once we substitute. Okay, so to verify a value for x as a solution for that equation, we can substitute and see if it equals 0. If it does, then that is a solution. If it does not, then it is not a solution. So if you want to, you can go ahead and complete problem B. It's the same concept. I'm going to hold that one off for now, and we're going to use that as a warm-up when we reconvene in class. Let's take a look at the last problem, problem 8. It says, for each of the following, write the quotient in the form a plus bi. So notice in a, b, and c, we have fractions. And what we want to do is we want to get rid of these fractions. Eventually, that's going to help us to simplify expressions by getting rid of fractions. And so we're going to do this with complex numbers. Now, what I want to look back at is 6D. Notice in 6D, we had multiplication. And when we multiplied, we came up with a real number. So if everything simplified, all the imaginary numbers disappeared, we were left with just a real number. We can actually make that happen and use that concept here in problem 8. So notice in the multiplication, the two complex numbers were exactly the same, except for one was the addition of the two terms, and one was the subtraction of the two terms. This is what we call conjugates. So these two terms, these two binomials or two complex numbers, are conjugates of one another. The first term's the same, the second term's the same. The only difference is one is an addition of the two terms, one's a subtraction of the two terms. Or the second terms are technically opposites. So what that allows us to do is use this concept to get rid of fractions. So how we do that is if I take a look at A, 8a, what I want to do is get rid of this fraction by multiplying by the conjugate of the denominator. So this would be 5 and I, but instead of 5 minus I, it's going to be 5 plus I. Remember, if I take a fraction and I multiply either the numerator or the denominator by something, I have to multiply both the numerator and the denominator by that same thing. The reason being because now this is basically multiplying by 1. Anything over itself is just 1. So I'm not changing the fraction. What I'm doing is rewriting the fraction. So let's multiply the numerator first. So I'm going to distribute here. 2 times 5 and 2 times I. So this becomes 10 plus 2I in the numerator. In the denominator, I'm going to distribute as well. So this is 5 times 5, which is 25. This is 5 times I, which is positive 5I. Negative I times 5, which is negative 5I. And then negative I times I, which is negative I squared. So now if I look in that denominator, I can simplify that denominator. The numerator is going to stay the same. I'm going to have 25. 5I minus 5I would just become 0. Negative I squared is negative 1. So basically the denominator is 25 plus 1, which is 26. Now, I'm close to having it into this form, but not exactly because I still have a fraction. But what I can do is I can split this fraction up. Remember, 26 is the denominator, so it's the denominator for both terms. So basically, I can write this as 10 over 26 plus 2I over 26, or 2 over 26I. Now I want to simplify that expression. 10 over 26, we can simplify this a fraction because both 10 and 26 are divisible by 2. So this is 5 over 13. Same thing with 2 over 26. This is 1 over 13. So we have 5 over 13 plus 1 over 13I. And this is the final result. Our A value is essentially 5 over 13. Our B value is essentially 1 over 13. And then we have I at the end. Let's take a look at one more example. Example 8b. So again, the same thing happens here. Oh, sorry, there's a typo in these notes. Let's change this to 2 plus I down in the denominator. So in the denominator, that should read 2 plus I. Now, if I want to get rid of an imaginary or complex number in the denominator, I need to multiply by its conjugate. So I'm going to multiply by 2 minus I instead of 2 plus I. I need to do the exact same thing to numerator and denominator. So multiply them both by 2 minus I. So what I can do here is I can do some distribution. So if I distribute 3 times 2 in the numerator, they're good, yeah. 3 times 2 will give me 6. And then I can take 3 times the negative I to give me negative 3I. Then we're going to distribute the negative I as well. So negative I times 2 is negative 2I. Negative I times negative I would give me a positive I squared. This is all in the numerator. Do the same distribution in the denominator, or same concept. So 2 times 2 is 4. 2 times negative I would be negative 2I. I times 2 is 2I. And then I times negative I would be negative I squared. So to simplify, I need to simplify the numerator and the denominator. The numerator, when I simplify, would become 6 minus 5I, combining those terms of I, plus I squared, which is negative 1. So plus a negative 1, we can essentially change to minus 1. In the denominator, I would get 4. The negative 2I plus 2I would cancel each other out, minus I squared, which is the same as minus negative 1. So essentially become 4 plus 1. Now, I can simplify the numerator a little further. 6 minus 1 would be 5, minus 5I, over 4 plus 1, which is 5. Finally, I can break apart my fractions. Let's break this apart into two fractions. So 5 over 5 minus 5I over 5. And then we can simplify here to get 1 minus I. So the final result would be in the form a plus bi, because we have the a value that's 1, a b value that is negative 1, and then I at the end. So in order to simplify fractions that have imaginary or complex numbers in the denominator, we have to multiply by the conjugate of that complex number in the denominator, and then we can simplify that fraction to get it into standard form. We will keep C in the notes and use C as a warm-up when we reconvene in class. Thank you guys for tuning in, and I'll see you soon.